Together, we'll explore the nature of intelligence. Intelligence for machines. So what is intelligence for machines? Intelligence for machines could be said as a product of information processing. Now, intelligence for human beings could be different, but for machines, it's just a product of information processing. When I say information, I also mean data. So you specify the properties of output information, and then you specify it as a function of input information. Then it becomes a computational task. And we are interested in computational intelligence. So this kind of computational task can be solved by algorithms. So the answer to a computational task is an algorithm. Now, what kind of algorithm? So we have a bunch of varieties of algorithms, and some of these has the ability to learn. So we express our algorithms in terms of dichotomy between the one that has a learning ability and the one that doesn't have the learning ability. So the algorithms that can learn, those are AIs. And AIs can have a program. I think we already know that we human beings are dangerous. The wealth of information and the growing knowledge that we have, it need only be misused once to end the entire project of humanity. Now, human beings are dangerous, and to that extent, AI is also dangerous. Now, the worry that AI is more dangerous than human beings, or the worry that AI is going to get away from us, this kind of worry is speculated by some computer scientists, non-computer scientists. So they think of ways of shackling AIs. That is the mistake. So I'm deeply unsympathetic to this kind of worldview. Now, the good news for the worried members of the planet Earth, those who are worried about AIs, is that our AI or machine learning or intelligent technology is not that far. I mean, we are not even at a level of human intelligence. We don't have any program that resembles a human level intelligence yet. But look what I said, word far. The metric behind the word far, the dimension of the metric behind the word far is not time. It need only be one breakthrough that can change everything. And we, first and foremost, are engineers and scientists. We can make that breakthrough. So to make that breakthrough, we need to understand what are the computational complexities of those learning algorithms so we can design better algorithms. Maybe at some point, those algorithms will design even better algorithms, and so on. That's how the progress of knowledge will proceed. Now, we would like to study this algorithm, and let me say that we'll be studying this algorithm in terms of the ones that has learnability. This learnability will be studied under two categories. Okay. So PAC learnability and APAC learnability. The PAC learnability, what does PAC stand for? Can anybody tell me?
Probably approximately correct.
Probably approximately correct, right? So the learning ability, one of those are probably approximately correct, and the other ones are agnostic PAC learnability, agnostic PAC. So I'll not give a very descriptive description or anything. I'll just tell you the gist of it now because you already attended 4 weeks of lecture, right? So we will study those in terms of loss. Okay. If a PAC learnable hypothesis class has this amount of loss, meaning less than the epsilon, then we say that it is PAC learnable. If it has more than that, probably it's not a PAC learnable algorithm. Now, with PAC learnability, there is something special about it. We suppose that there's no sample error in PAC learnability. It is rather a very strong assumption. We'll revise this assumption for agnostic PAC learnability. Now, we suppose that there is no sample error. Usually, there will be a term here that will have some sample error. So there is no sample error in path learnability. When we don't have it, because when the realizability holds. In short, I'm writing it as realizability holds. What is this realizability? It simply means that it doesn't have any sample error, right? So sample error is 0. For agnostic path learnability, we are a little bit more practical. So we understand the real-life trade-off. So instead of claiming something impossible, which is not exactly impossible, but mostly it is, because we never know that there will be some sample error or not. So we are using a much more gentle approach. So the important distinction or generalization for these two kinds of learning ability I'd like to make is that APAC learning ability is a generalized version of PAC learning ability. Because what we're doing here over the hypothesis class, we're trying to figure out that particular one hypothesis that has the minimum error, and that minimum error for PAC learning ability is 0. So we can, of course, claim that APAC learning ability is a generalization for PAC learning ability. Now, we'll be studying a bunch of those ideas along the way. Now, I don't want to discuss a lot about the ideas because you've already attended 4 weeks of lectures. But the goal for today's class is to solve all the problems that we have. So we will solve that, and any idea from the previous lecture that pops up, I'll briefly discuss, at least in a way that is easier for you to comprehend. Okay? Now, we'll go to the problem set, right? Okay, so I guess this is the first problem, right? 2.3, isn't it? Alright, so an axis on a rectangle classifier in the plane is a classifier that assigns the value 1 to a point if and only if it is inside a certain rectangle. This is the rectangle we're talking about. And then this rectangle, you see the region, right? And this, there's a smaller rectangle inside. I'll tell you the question as a student because the whole thing is so messed up, and actually not messed up, because this is the standard way of describing a problem, alright? But what I will do, instead of reading it out in the class, because our class time is really short, what I will do, I will explain the question so that you understand, and then we'll try to attack this problem. Now, okay, so the first one says that let A be the algorithm that returns the smallest rectangle and goes in all positive examples in the training set so that A is an ERM. So our goal is to prove that the algorithm A is an ERM. Okay? Now, much noise. Okay, so let me describe the problem first, okay? The idea here is that we have a bunch of pluses, okay, and also a lot of minuses, right? Now, we would like to, our algorithm, consider our algorithm to be a rectangle, okay? The rectangle is an algorithm. So the way we'll do is that we will use that rectangle to catch all the pluses inside and minuses outside. That's the simple idea. Now, how can I do that? Looking at this picture, it's pretty easy. Just draw a rectangle, right? So all the pluses are inside and minuses are outside, right? Okay. Now what if we have some minus here, or some complicated challenge, like you want to fit that rectangle for all the pluses? What's going to happen is some minuses are inside, and what we say that we have some sample error, right? Now, if we have some sample error, that is a problem, because our question is asking that find the ERM. ERM is the one that doesn't have any sample error. Now, let me draw even smaller rectangle. Now, probably we don't have any sample error. Here we have some sample error. Pluses, some minuses, right? But inside of it, there's no sample error. You okay with it? Cool. Now, for the first problem, 2.3, if realizability holds, then the sample error is 0. Right? If the realizability holds. Now, if you look at the picture or diagram, you can tell that the smallest rectangle will have 0 sample error. Right? So, smallest has the smallest one will have 0 sample error. Now, we want to prove that that is an ERM. What is an ERM? Let's see the definition of ERM. By definition of ERM, we can say that ERM, the sample space, belongs to the argument, which belongs to H as So the idea for ERM is that it tries to find the minimum of the hypothesis from the class of hypotheses that gives us minimum error. And we know for ERM estimator that minimum error is 0. Okay? So this minimum error is 0. Now we can say that our algorithm A is an ERM estimator or ERM. Okay? So A. Does it make sense? Yeah, I'll ask a specific question. Yeah.
I can get it.
Okay, so we're using an analogy here. Okay, we know if the realizability holds, then the error on the sample space is 0. Correct? Our training set is 0. Now, if we draw a rectangle that is the smallest, that also gives us 0 sample error, right? Our training error. Now our goal is to prove that our algorithm A is an ERM learner. So what is an ERM? The ERM is the hypothesis that gives us the minimum error over the training set. You get the idea? Now for an ERM estimator, we know that the sample error of the sample space is 0. Now, if all of that satisfies, and if we compare and take it as an analogy that this gives us 0, and ERM also gives us 0, then can we conclude that our algorithm A is an ERM? That is the analogy that we use. Okay.
I didn't understand the relationship of A1, B1, A2, B2, and X1, X2.
Oh, you're talking about the labels. Tell me what you're talking about.
What do these signify? A1,
It's just the rectangle, like A one side, B other side, A1 on the other side, B1 on the other side. You know, it's just a rectangle. Now the problem with this approach, I'm trying to make it as simple as possible. I'll present this idea in the simplest possible way. There are 2 ways to do it. In fact, I myself did it in both the ways. One of the ways is being very pedantic and following all those notations and making it mathematically beautiful, but for common people it's dangerous, right? So the way I will present it, is make the idea simple and clear, and I will try to keep the notation as simple as possible so that you don't miss the main idea, right? So all this means is the sides of the rectangle, like one side is A1, other one is B1, and one is greater than the other, so it makes the whole calculation complicated. I don't want to do that. But it is the same thing, and the book has a little bit of ambiguity, right? Which I think only Shai-Ben-David knows and no one else, right? So we will try to make a comprehensive approach and an easier one, correct? Now we're done with the first part of the problem. Now the second part here, the idea is show that if A receives a training set of size this, with probability of at least 1 minus delta, it returns the hypothesis with error of at most epsilon. Now, does that ring a bell? You see that at most epsilon and the probability 1 minus delta, all it's suggesting is that it is a packed learnability. If you look at the definition of packed learnability, it's not a complete definition though, but it suggests that it is a packed learnability. Now, here our goal is to find out the error region, and then from there on, I mean, reading all of these, that's the idea. I'm not going to read everything out here because the solution approach is already given in the hint. So we like to solve problem 2.3, right? So it's basically a continuation of the previous problem, right? So what do we have? We have a bigger rectangle, and then we have another rectangle inside, and we're interested to find out a better rectangle that doesn't give us enough error, or pretty much no error, because we already proved that our algorithm is a ERM asymmetric, or ERM algorithm, right? So we have a bunch of pluses in it, pluses, right? And then we have minuses on this curve, and then the minuses are pluses or minuses, okay? Alright, so we are interested to find out how many ways we can make mistakes in placing the algorithm. Okay? So if you place this our algorithm or rectangle slightly on the left, right? Then what's going to happen? We get some error from this side, right? If we place it a little bit up, we get some error here. So for this algorithm, there are 4 ways to make mistakes, right? Because it has 4 sides, and we need to find the optimal position for that. So one way to make a mistake is like on this side, okay? All right, so I'll use another color probably. So I'll just draw them first. So we'll just move on this side. This side. So, right. So depending on the position of this rectangle, we can make mistakes in 4 ways, right? Are you convinced with this idea? All right. So what I'm saying that this is the error region, and it has an error of epsilon over 4. This is my error region, and it has error of epsilon over 4. This has error of epsilon over 4. This makes error of epsilon over 4. Now you might be wondering why epsilon over 4. Okay. So the
One side of the
what?
rectangle.
4 sides, right? Yeah. That's a good idea, but what if we have like 1,000 sides? Okay, so for this algorithm, what did you say? We can make error at most epsilon, right? You remember that from the question? So if you partition this error into 4 different triangles, that's what it becomes, right? So if we can allow at most epsilon error, then what's going to happen? So we allow our error for this one on this side, on this side, this side, and this side, and then finally we get the perfect predictor. Does this make sense? Right? So how do I write it? Let me write it mathematically. So I'm calling this to be R1, right? R1, R2, R3, R4. Now if I union R1, R2, R3, R4, that gives me R, which is a perfect prediction, meaning it doesn't have any error. Does this make sense? R4. Yeah. So that's how we get the perfect prediction.
R1 is the part without fake errors.
R1 is what?
R1 is the part in the first rectangle without the error.
No, this has error. So 1 minus epsilon is the one that doesn't have error. Okay? 1 minus epsilon over 4. 1 minus epsilon over 4. Does it make sense?
R1 is the rectangle. R1 is a rectangle which has epsilon by 4 error.
R1 is the box.
Yes.
It's not the errors are not
Epsilon over 4 error, and this is 1 minus epsilon over 4 correct. Okay? Labeling correctly. And, that part is mislabeled. Now, let me also say that, how about I write it here? Now we have our air, and then what I'm interested in doing is I'm going to distribute that air. I want to use R2 Now, this is the total error, right? I can write the word total or whatever. Yeah, total. Total error, and the error, total error is the error of this region, and that region, right? Now, if I take the union bounds, did you learn about union bounds?
Yes.
Great. Okay, so we distributed that, and then it becomes less than equal, right? That means the union bounds that we learned. Now, that is the total error. We distributed it all over the smaller rectangles that we've drawn. Now, what I'm interested in doing now is I will find out the probability for R1. Okay. So let me calculate it for R1. So the probability we sample it from D via IID, and then we have the sample that belongs to R1. What I'm calculating now is that our data point so what we're interested in finding out now that these are all sample points, right? Each data point, right? So the idea here is that what is the likelihood that a particular sample point belongs to the R1 region or R1 rectangle, okay? Or R2 rectangle, R3 rectangle, right? That's what we're interested in finding out now. Now let me find it out. So 1 minus epsilon over 4 for 1 point, okay? For 1 point. 1 minus epsilon over 4. Now, how many points do we have? Tell me. How many points do we have? Can anybody tell me how many points do we have? Yeah, I mean, you can see it from there. We are sampling from the distribution D, which has the n number of points. So we can say that we have 1 minus epsilon over 4 n. Okay? The total number of points. And that gives us, so you're familiar with it so far, right? I mean, yes, it is. But if you are not, you can think about it in terms of Taylor series. Okay? If you're familiar with Taylor series from your calculus class. So yeah. Now, what I'd like to do is, now let me tell you this: the probability of getting a misleading training set which gives rise to a bad hypothesis like this R1 has error epsilon over 4 is the probability that the training set points also falls in that region. So basically what it is telling us, let me write it mathematically. So this is my total problem, total number of errors that we can allow, right? Because that's the total error epsilon, and we distributed it for the smaller rectangles. With this amount of error, what is the probability that we can accept? So this is for the total one, right? Not for long run. For the total one, we're calculating the probability, and we just calculated the probability for one rectangle, which is that one, right? So what I do now is I write them 4 times. What is that? So, yeah. the short time basically is 4 to the power of 4, and that is our delta. Right? So far, we are okay. Any questions?
So that basically represents the error for just R1.
For R1. That not error. What is the likelihood that a particular sample in that R1 will be R1? Okay. I mean that falls into the R1 region. Right? So we have that. And now, like I said, what we need to calculate is the sample complexity. Okay. Now from there on, now delta is going to be equal to right there 4 power and 4. So if we calculate, we end up with an m, and that has 4 over epsilon ln. This amount of complexity. So the question asks us to find out this time, this sample complexity and the errors and all of that. And as per the instructions, the things are given. I said, so I've done pretty much everything this question asks. That's R2 of 2.3. Now what I'm going to do is I'm going to work on part C. Part C doesn't tell us a lot. It just tells us that that if this time for part for part 3 of 2.3 it says that we're going to do it for previously we've done it for 2-dimensional, okay? Previously this one was for R2, meaning 2-dimensional. Why 2-dimensional? You can easily picture it from here, X and Y, right? Now for part 3, they're asking to calculate the same time complexity, but this time for RD, D-dimensional, right? Now that's what we like to calculate. But let me for reference, we'll just write the time complexity that I wrote in there. Okay? From what? From part 2, what we got is m 4 over epsilon ln 4 over. That's what we got from part 2. Now let's analyze this carefully. What we're doing for this one is that we have 4, meaning we have 4 rectangles. And why 4? Because for each dimension, we needed to find the maximum and minimum for each of the data points in the sample space or training set. So that's why for each of the dimension, we have to do it for twice. All right. Now for D dimension, what we do, this one was for 2 dimensions. So for each dimension we go twice, so we had like 4, right? For D dimension, we do is we go 2, right? Now, so we can write that m is greater than or equal to 1 over epsilon over 2d ln 2d over the. Does it make sense? Alright, so we are done with part 3. Now, this problem has part 4 as well. Part 4 is fairly simple. All it is asking is the runtime. Now, you're familiar with this big O notation, right? From your algorithm class. I believe, you're done with your algorithm class. So, for part 4 of this problem, we write for runtime. We have this big O notation. And now, we'd like to calculate this runtime for this one. Now, we're doing it for D dimensions. So we write D, and for each of the dimensions, what we do is we traverse through M points because we have M points, right? M sample points. So when we traverse through, what we exactly try to find out with this algorithm is we find out the minimum and maximum values among the polynomial instances from the training set. So we have M data points. So this is M. Now that's the runtime for this algorithm. So we are pretty much done with problem number 2.3. Alright. So we'll move on to the next problem, which is basically the next chapter. This is turn it off. The AC. Now we're going to do chapter 3.2. So this is our algorithm or hypothesis. It's a singleton algorithm. I will explain what a singleton means. And this part, we have, you can pretty much say we have two parts. This one is the negative hypothesis, marked as H minus, and this one has a positive hypothesis. Now, this negative hypothesis will capture the points that are labeled as negative or negative points, correct? And this one will capture the positive points. Okay. Now, altogether, it will pretty much capture everything. Okay. So in our let me actually write. Okay. Now, let's consider, this is my training set, and we have a bunch of points in here, right? So many points out there. And let's say all of these are negative, okay? But there's one guy that is positive, and then all of them are negative, right? Now, that single guy who is positive among all of the negatives is the guy who we call singleton, right? In our society, we do have some singletons, right? I'm not saying it's a bad thing to be singleton. It's not a good thing either. Now, our goal is to capture that guy, or even not to capture that guy, basically. What we want to find out is describe an algorithm that implements ERN rule for the learning H singleton in the realizable setup. Now, what we are assuming here is realizability, first thing to notice, and then we'd like to prove that this is an ERN. Okay? Does it make sense? Now, let me work it.
So the singleton means outlier.
Yeah, you can say it like that. When you look for anomalies or outliers, it's pretty much the same concept from the machine learning ideas. So what we're doing now is just theoretical machine learning. So the mathematical intuition that you develop in solving all of these problems will basically make you a deep thinker when it comes to the real-world practical engineering approach. Now, this course is fascinating because it has enough theoretical components. If you're willing to go to graduate school, you'll thank me, correct? in machine learning. But if you don't want to go to graduate school, still with this amount of X-ray kind of vision when it comes to real-world engineering, you'll pretty much dominate the field once you have the practical skills of implementing. But you see the bigger vision that other engineers won't be able to see, right? So that's where you get an edge than the other people. Okay, so we're going to solve the singleton problem. Now, let me describe the idea over there. No, the idea is clear, right? Now, if I choose, let me write the singleton hypothesis class. Now, we have basically two hypotheses, right? One is this, the other one is that. So this one captures all the negative ones. This one captures the positive points. So let's say if I choose this positive hypothesis over here, as I'm calling it H plus, okay? Now, if I choose H plus hypothesis, what's going to happen is it's looking for plus signs, right? So what it gets is a minus, so it makes an error, right? All the way it makes an error. Only time it doesn't make an error is when we have a plus. So this gives 0. Each plus gives me 1 only in this place, right? So we are making a huge amount of error with this hypothesis, right? Now, let me consider for h minus. For h minus, this one gives 0, right? Because it is plus. But if I choose h minus in here, it gives you 1, right? So if we capture all these points all the way, suddenly a guy pops out, that single guy, and then all the minuses, right? So which one is the better? Which one is better? Like using this one, we make less error, right? Okay, so, all right. Now, probability that x plus, I mean this singleton, x plus belongs to S. S is my whole sample space. Okay? And the probability that x plus doesn't belong to our sample space is 1. Because you know the total probability is 1, right? Now, what I'm interested to find out is x plus doesn't belong to S. If that is the case, what we have is probability of x plus belongs to S. Okay? I just changed the size. Now, for this one, we're claiming that x plus belongs to S. Meaning x plus belongs to S. If that is the case, for choosing the negative hypothesis, we have an error, right? We have an error. Now, what is that error? At most, we can take epsilon, right? So that error for choosing h minus is epsilon, right? Now, probability x plus doesn't belong to S. Or for 1 minus epsilon, we can write this as less than or equal because we know that at most this amount of error we can make. Now for m primes, this is what we find. Okay. Now, power minus epsilon m, which is equal to our delta, probably sampling from a non-sampling. Did you get that first? Okay. So this is the error that we can make mistakes for choosing our hypothesis h minus if x plus belongs to our training set. Right? So that error is epsilon. Basically, at most we can make epsilon error, so it's less than equal epsilon. Does it make sense?
Here the mistake is choosing the plus.
Yes. I mean, having plus, not choosing. It's there, right? We're not choosing. So from there we can come to the sample complexity. Remember epsilon having. Right? So from this relation we can find out this sample complexity. So we're done with problem number 3.2. Now what we'll do is problem number 3.3, which shares a lot of these things in common. You want to see the question first, or you want me to guess first?
Simple.
I will quickly show you the question, just to intimate you properly. Any question? You guys are as silent as the ask questions. Okay? Yeah. I mean, feel free to ask questions. I mean, hopefully I'm not that scary. Okay? So ask questions. So I can see it.
We are afraid that if we have questions, we won't be able to finish the later 5 questions that are still left.
Oh, really?
Yes.
The last
Two problems.
Are you going to finish all today?
I mean, if not today, never. And I can finish it ever, not today. So because after the break midterm, so you don't have time, I don't have my time, so my time is as valuable as yours. So the wise thing is to get it done by today, not today. Alright, so is this what we're going to do now? 3.3? Are you understanding my lecture?
Yes, sir.
So, yeah. Alright, this is the problem, okay? So it's a concentric circle. Now, you know what a concentric circle is, right? And it has a certain radius, and it has the indicator function. And we like to prove that this is calculatable, and we know that we need to calculate calculatably what we essentially look for is sample complexity. That satisfies with probably making mistakes epsilon with making mistakes at most epsilon with probably 1 minus delta. That's what the calculatability is. Now we're going to do it quickly this time. Am I going slow?
Perfect.
Slow?
No, perfect.
Okay, so okay, so what is the idea here? We have a circle and maybe another circle, right? Now we have a bunch of minuses, even a lot of minuses outside, okay? And we have a bunch of pluses inside. Now, that's the same idea as we did for rectangles, or maybe not, yeah, pretty much similar. So we'd like to capture all the pluses with perfection, meaning no error in the sample space. Now, it could be the fact that we have a few minuses there, right? Just a few, so we take even smaller circles, right? If we take bigger circle, what's going to happen? We make more mistakes. The smaller and smaller circles we take, better approximation we can make, right? Now let's say this is the angular region. Okay. So if our samples are if we're sampling from the angular region, we're likely to make some mistakes, right? Because we have some minuses in it, right? Okay, let me write that. So, probability x doesn't belong to the shaded curve or angular region is less than equal, is greater than equal to epsilon. Meaning that if it doesn't belong to this region, we can go all the other regions and make so many mistakes. So the error is greater than epsilon, right? Now what I do is I take minus on both sides, and then that changes our inequality. And I take 1 on both the sides. And this relation will be helpful for us. So we just split it there, okay? Now, we look for the total probability constant again. And then what we know is if our sample belongs to shaded curve class, if that doesn't belong to shaded curve, then its probability 1. Now, if it belongs to the shaded curve, then what we have is 1 minus x doesn't belong to shaded curve, right? Now, this is what we've got, right? Look at the relation we created. For this, we have 1 minus epsilon greater than 1 minus epsilon, right? So in place of this, we can write 1 minus greater than epsilon. Now, that's where 1 point, okay? Now we look for endpoints. Probability for endpoints. Xi, because we have so many i's in it, that belongs to the shaded region, is going to be less than 1 minus epsilon for endpoints. Now for that, we can just calculate it easily, as we've done previously, is equal to w, right? So we calculate m, and that gives us number. And that it proves that it is a text learnable algorithm. Does it make sense? Any question? We're done with 3.3. How many problems do you left?
Up to 3.4 there are
3.4? Only?
and
3.4, and there are some problems.
You can find even the definitions, right? You want me to write down definitions for it?
We can find definitions ourselves.
the last 3 questions can be found in the book.
Alright, so can you turn on the air conditioner?
The remote is outside.
Alright, this problem is a little bit tricky, okay? So I'll try to explain it as easily as possible. Alright, so what we're going to find out is a Boolean conjunction, correct? A Boolean conjunction that can capture, which will work like an algorithm for us, and capture all of these sample points and training points. These are the training points. Training data. Now, we have our X or instance space, and then we label it Y. We will label it 0 or 1. So we have a bunch of literals, like x1 all the way to g. Now, these literals are sort of defined by this function, x, and its negation. It can be written as x1 wedge x2. So, x2 bar. So from here, what I'd like to do is to construct our training set first, and then find out a hypothesis, which will work for all of these problems. Now, what I'm interested in doing first is writing down this. Let me write down all the points that I have. So, looking at the points, we can figure out our algorithm. So, 1, 1, 1. That's the first point. 1, 0, 1. 1, that's the second point. Then we have 0, 1, 0. And then 1, 0. These are my training points, right? This is problem number what?
3.4.
When is it there?
6:45 or
Alright, so we're pretty much done. We don't take much time. Alright, so you understand what it is.
The left side is x and 0 is the y.
Levels.
Right? So this is my x, and that's y. These are x, y, x, y. Right? So looking at these data points, we can construct a set for training or samples, right? Training set or samples. So let's construct. We consider that to be a vector. A and y1 is our output. goes all the way up to m, because we have m data points or n vectors. Right? So that is set for training our sample space. Now, let us set the goal first. What is our goal? Our goal is to find a Boolean conjecture that is made out of literals that can work for every single class, every single time. Okay? Now, so let's consider 1, x2, x3, x4, x6, negation for a couple of them. So, or even I can take a little bit longer. If our literal is too long, the chances are we make more mistakes. Again, if our literal is too short, chances are we make more mistakes again. Right? Now, we need to find a literal of appropriate length that works for all these subplots. Alright, so what do I mean by that? It doesn't work. Let's see. x1, 1 meaning it's yes, or 0 means it's negation, right? So does this work for this one? x1, x2 doesn't work, so it's gone. We're missing 1 point. So the mistake, missing 1 literal, is a huge mistake, alright? So we make a huge amount of mistake if we just miss 1 literal. That goes wrong. Or because of that 1 literal, we can miss thousands of data points. If we have billions of data points, we're right? So we need to look for an optimal length and also with correct combination of literals. Now let's see. Let's try to construct a literal for this one. Okay. Now this is x1, but you see that this is wrong. Okay. This gives us wrong output. Many wouldn't even care about it. What we care about is this one. This is my output, and that says yes. Now look for this one. This one is x1, then x2 bar, right? And then x3. That's the literal we get with correct output, right? This is the wrong output. Now let's look for this one. Okay? This gives us wrong output, this gives us wrong output, this is correct, and this is correct. Look for this one. What we have here is x1, x2 bar, and x3 bar. Now we cannot have literals that works for some data points and that doesn't work for some data points. So that is our contradiction. And what we do is we cut it off. We throw away that part that creates a contradiction. We take this part. Now you see. Okay. Now if these two matches, we get yes. These two matches, it doesn't match. We automatically get no. These two matches, we get yes. Which tells us that if this is our literal, our current literal this time is going to be, our current literal is going to be what? x1, x2, negation. That is my correct literal. With that correct literal, I can go write about all the subpoints. That is the PI, right? Now we would like to construct an algorithm with that. Okay? We have H0, correct? That is my algorithm, let's say. Okay. And then in the question, they also said that x1 and its negation is also allowed, right? x1 had a wedge and its negation, or x1 and its negation is also allowed in our algorithm, right? But if it is allowed, what does it tell us? It gives us 1, it gives us 0 for the same x1. It is our contradiction again, but that fortunately gives us a negative one, meaning it's wrong, okay? But we can allow that in our algorithm. Now, with that idea, let me construct an algorithm. That is my algorithm. Now, why it works, let's see. Right? Now, if you look at this point, right? It's 1. So the interesting thing about this algorithm is that if we take this, we cancel the other one out, right? So if I'm taking x1, we cancel, even if it's different color, we cancel x negation, all right? X1 negation. If I take x2 from there, x2 negation, we cancel out x1, right? So that's the beauty of this algorithm, that you pick one of them, but you allow, when you design the algorithm, you allow x1 and its negation over here, because that's going to give us the mistakes. So one trick that works for all the data points, if both of them are true, then we get a mistake, because that's the condition that cannot happen. What can happen is one of them, and that's how we find the correct literal for all the points. And this algorithm can capture up till, this can capture all the data points of the sample, right? So we have a beautiful algorithm now. Now, if you look at it, what's going to happen is that this algorithm, let's say I get yes for this one as well, right? Meaning we are taking x3 and its negation. Then if that happens, what does it give us? -1. This is the all negative hypothesis, but from this all negative hypothesis, we can construct a hypothesis as we just constructed right now. This is the hypothesis we found to be true for all of these given points, right? See? Right? So this H0 gives us all negative hypothesis itself, but from this H0 we can construct a new hypothesis HM that gives us the correct hypothesis. Now can we now say that this is the area and this is the factor negativity, this is everything? Now we are interested in finding out the sample complexity for this algorithm. Now before, alright, so what is the sample complexity for factor negativity? By default, what we have for factor negativity is this. This is what we have for factor negativity. Now, previously, we had a certain size for our hypothesis class A, right? What is the size this time? Let's calculate the size. We are interested in finding out the size of our hypothesis class. Now, this is my hypothesis class, okay? And that is the algorithm. And can anybody tell me what is the size of it? So, alright, so we allow x1. We allow its negation. Or it might happen that we didn't capture anything, right? So the size for this algorithm would be 3, and we go all the way up to d points, 3 to the power d, and then this all negative hypothesis itself, another hypothesis, we include 1. So that is the size of our hypothesis class. So with this size, you can calculate 3 to the power d plus 1. Alright, so so we have x and its negation, and we can choose nothing at all. So, and then we have our all negative hypothesis. So, okay, so when I distribute this, as I distribute it, what's going to happen is 3 to the power d. So if you have log x plus y, then log x plus log y will be less than that, less than equal to that. You know that from your logarithm. So take the d side, and then we have d. That is the answer. So I think I've pretty much solved everything. So the whole problem set is solved. Now, maybe with problem number 6, I can talk about it. Problem number 6 from the assignment, not from the book. So I can just talk a little bit about it. Maybe I'm not going to write everything down because that's something you can solve with the help of the tool. So what it is saying is that look at the number of training samples and larger than whatever. I mean, basically, this sample complexity, the ERM, is a pack learnable algorithm. I'm pretty sure you can do it. Okay? From the book. It just proves that you have this amount of sample complexity, so it is a factor in it. So I believe that you can solve it. Or do you want me to show you? No. Great.